Hello, everyone. Welcome back. In lecture 10, we're going to discuss Gibbs phase rule, one of the most important rules in thermodynamics. When we talk about the Gibbs phase rule, we first have to define what is a phase. Phase is a region of materials with homogeneous molar quantities. Homogeneous, we mean it depends on a matter of spatial or time resolutions observations, right? So typically, in material science, we define homogeneous in terms of X-ray. But of course, if you go to space, well, homogeneous will mean different things, right? If you go to atomic scale, it means also different things too. Okay, so for homogeneous and equilibrium system, we have the Gibbs-Duhem equation. That all the potentials are related in a homogeneous equilibrium system in the form written XA dYA, with XA for the molar quantity, YA for the potentials, for the conjugated potentials. So a phase would then be represented by this equation, right? It's homogeneous. So we have C+2 variables, okay? And because of this constraint, all the potentials are not independent. So we only have C+1 independent potentials. So if we construct a space of potentials with C+2 potentials, a C+2 dimension space, then in that space, C+1 dimension feature would be a phase. So each phase would be C+1 dimensions feature. For example, if it's a one component system, C+1 equals 2, the two-dimensional surface would be in a three-dimensional potential space, would be a phase. Okay, so we can add more potentials, right? We can add instead of volume, we can add stress. We can add electric and magnetic fields. So we can add more potentials. But in most of the cases, at least when we teach in thermodynamics, we talk about the C+2 potentials. That's temperature, pressure, and chemical potentials of each component. And of course, we may also have internal variables, right? The system may not have full equilibrium or freeze-in condition, as we talked about it before. Then you could have more dimensions, right, for freeze-in conditions. But let's focus on only the C+2 C+2 potentials with C+1 dimensions feature represents a phase in this C+2 dimension space of potentials. Okay. Now we get to heterogeneous systems. Talk about equilibrium. That's actually what Gibbs did when he presented the thermodynamics for multi-component systems. So we talk about a system with more than one phases now. Okay. As we talked about it before, a phase is with a homogeneous molar quantities. So of different phases, that means the molar quantities are different. So in order to differentiate the molar quantities, we normalize them. Okay. For phase alpha here, we still have molar quantity, molar entropy, molar volume, and mole fraction. They're just the entropy divided by the moles of that system, and the VM get moles, so it's a molar value. So this is people sometimes use called intensive variables, but I don't use them anymore. As I mentioned before, we call them molar quantities. They just normalize the molar quantities. So if we believe this system with many phases are in equilibrium, okay, then we do a virtual experiment. So if we move some molar quantity, d psi, from phase alpha to phase beta, right? So it means here we have alpha phase and beta phase here. We move some quantity of molar quantity from alpha phase to the beta phase. Then the internal energy change of the system will be what changes for the alpha phase, what changes for the beta phase. Add them together. So du equals to du alpha plus du beta. So now we move entropy. So we move some entropy from this to there, from alpha to beta. And we know that the du would be equal to temperature times ds, right? But now for the alpha phase, ds is negative because we take some ds out of alpha. So it's minus T alpha plus minus T beta times ds. Okay. So that's one virtual experiment. Then we'll do another virtual experiment, move volume. Move some volume from alpha to beta. Okay, we know that du equal to minus p times dv. Okay, so it's move the negative dv from alpha, next time negative becomes positive. You have p alpha is positive minus p beta negative. So we can all move the mass too, right? We move dni from alpha to beta. So then we know the internal energy is chemical potential times dn. So it'll be minus mu I alpha because we remove dni from alpha phase and add into the beta phase as mu I beta here. Okay. Now we know that if it's equilibrium, that change shouldn't really not affect the internal energy. Okay, as internal process if they are equilibrium. Okay. So that means we immediately get that equilibrium conditions, temperature has to be homogeneous, pressure has to be homogeneous, and chemical potential has to be homogeneous. As we talked about before for the homogeneous phase. So I get the same conclusion. Okay, so each potential is homogeneous in all phases this time, not only in this homogeneous system, but in every phase which are in equilibrium. If all the phases are in equilibrium, they must have the same temperature, same pressure, and same volume, same chemical potential. Okay, so now remember that that means the Gibbs phase, the Gibbs-Duhem equation must apply to each phase, right? Okay, so each phase has a Gibbs-Duhem equation. Each phase has different molar volume, molar entropy, molar volume, and composition. Okay, we normalized by the n alpha, number of moles of that phase. We get Sm alpha, Vm alpha, and Xi alpha. Okay. But because all the phases are equilibrium, when we make that, that means each time we add a new phase, we add one constraint. Because if the phases are equilibrium, the dt has to be the same in both phases, in all phases. D minus B and D mu I must also be changed the same too. That means for each phase, I have one Gibbs-Duhem equation. Okay, that means one relation or constraint among the potentials. So every time we add one phase, we add one more constraint. That means the number of independent potentials will decrease. Okay, that's where it gives phase two. So we have C plus 2 potentials in the system, and each phase has one Gibbs-Duhem equation. So P phase, that means number of Gibbs-Duhem equation will be P. Okay, so it's very clear now. The new here is number of potentials that can be changed independently without changing the number of phases in equilibrium. And where C is number of independent components. The very important is the independent components. Okay, that means it can change independently. So that will give us number of chemical potentials. And the number 2 here is temperature and pressure. Are the two potentials. And P is number of phases in equilibrium. Each phase gives one Gibbs-Duhem equation. So number of Gibbs-Duhem equations among potentials. So it's all potentials here. That means, of course, that means the result of this equation is also potential. It's number of potentials that can be changed independently without changing the number of phases in equilibrium. So when talk about phase equilibrium, the two-phase equilibrium, as I talked about just the 2 slides before, that they must have the same potentials, right? Homogeneous potentials. So again, let's go back to this C plus 2 dimension space of potentials. That's the temperature, pressure, and the C chemical potentials. For single phase, P equal to 1, then nu equal to C plus 2 minus 1 equal to C plus 1 independent potentials. So that's a C plus 1 dimensions feature. That's when we used to define the phase. Now if we have two phases, P equal to 2, then the number of independent potentials decreases by 1. So C plus 2 minus 2 equal to C. So it becomes C dimensional feature. So now if you think about if C is equal to one component, okay, that means a line, right? That'd be a line. Now, if it invent equilibrium, there's no independent, all the potentials are fixed. Okay, then P max, that means to solve this equation, we get P max equal to C plus 2. And the max number of phases can coexist in equilibrium in a system is 0. It's C plus 2. So number of phases is C plus 2. There's no independent potentials anymore, or potentials are fixed. So you get 0 dimension feature. That's the point. Okay, that's the point in the C plus 2 dimension space of potentials. However, if you look at the literature, people often use Gibbs phase to talk about degrees of freedom. Well, in principle, they are right. However, a lot of confusions here. The reason is because, as I emphasized here, nu equal to C plus 2 minus P is about number of potentials, because all quantities here are potentials, or the relation among potentials. Let's give to him equation. It's about the relations between the potentials. However, the degree of freedom, it means what you can change freely. Okay, that means independent number of variables in a system. For a C plus 2 component, C plus 2 system, as C components and temperature and pressure, there are always C plus 2 degrees of freedom. You can change. That's represented by the natural variables in the system, or in the combined law. Okay, because in combined law, we always see you have C plus 2 independent variables. So that means you can change them independently. Okay, so you can do all model quantities. That's like internal energy. It's entropy, volume, and Ni. You can change them freely without change the number of phases in the system. It only changes the fraction amount of the phases. Okay, it doesn't. You can still stay in the same number of phases in equilibrium. By changing the C plus 2 variables, they just change the relative amounts of each phase. You can have a mixture of the potentials and the components as to represent the independent variables of the system, the degrees of freedom. For example, if you use Gibbs energy, now you have temperature and pressure as the 2 independent variables, then the other ones compositions. Other independent variables are the compositions. The Tp and I. So it's all about the natural variables. However, we cannot change all the independent variables to potentials. That's because we have Gibbs-Duhamel equation. Okay? So because Gibbs-Duhamel equation says that in a system, in the equilibrium system, potentials are related. Related if it's homogeneous, it's one equation. If you have n phases, p phases, there will be p such equations. Okay? So that means when we at least need one molar quantity to define as independent variable, usually we use the size of the system as independent variables. So it's very important that Gibbs phase rule and degrees of freedom are two different things, even though they have some connections here. Okay, Gibbs phase rule is purely about the potentials. It's the number of potentials that can be changed independently without changing the number of phases. At degrees of freedom of a system are the independent variables one can change without changing the number of phases. You can say that too, but these two are represent different things because degrees of freedom in an equilibrium system never changes. It's always C plus 2. Thank you. See you next time.